Hi everyone. In this lecture, we will explore the two types of quantifiers which were mentioned in the previous slides. As mentioned previously, quantifiers are symbols used to denote the estimation of the quantity for a predicate variable. There are two types of quantifiers. Universal quantifier, which is pronounced as for all and is represented by the reverse A symbol. The second one is called the existential quantifier. It is pronounced as there exists and is represented by the reverse E symbol. Let us start by discussing the first one, universal quantifier. As stated before, it is represented by a reversed A symbol. Consider a statement for every x p of x. This is called a universally quantified statement because it means that p of x exists for all values of x. It is represented as the expression reversed A x p of x. Note that this expression is true only if p of x is true for every x and false if p of x is false for at least one value of x. This expression is pronounced as for every x p of x, or for any x p of x, or for all x p of x. To understand it better, let us consider an example. P of x be a statement x is an honest man. The universally quantified statement for the same could be represented as for all x p of x, which corresponds to the statement for all x is an honest man, or in simple English, every man is honest. If we have the universally quantified statement for all x p of x, we can say it is true because p of x is true for all values, which also means that it is false if p of x is false for at least one value of x. A value that makes p of x false is called a counterexample to the statement for all x p of x. For example, considering the statement for all x belongs to R, x square minus 1 is greater than 0. This statement is false because in this case where x equals to 1, proposition x square minus 1 equals to 0, which makes it not greater than 0 and thus false. This means x equal to 1 is a counter example to for all x square minus 1 is greater than 0. Now let us discuss the second one, existential quantifier. As stated before, it is represented by a reversed E symbol. Consider a statement for some x p of x. This is called an existentially quantified statement because it means that p of x exists for at least one value of x. It is represented as the expression reversed E x p of x. Note that this expression is true if p of x is true for at least one value of x and false only if p of x is false for all values of x. The expression is pronounced as for some x p of x, or for at least one x p of x, or there exists x such that p of x. To understand it better, let us consider an example. Let px be a statement representing x is an honest man, and we can say the existentially quantified statement for this above statement can be there exists at least one x such that x is an honest man, or in simple English, there exists at least one honest man. If we consider a predicate p of x and if we introduce quantifiers to it, then we say that variable x becomes silent or bounded. Moreover, the predicate becomes a proposition. Let us now discuss the principle of compound quantification, wherein there can be multiple quantifiers nested in a single statement to depict quantified relations. If there are multiple quantifiers in a predicate, then the order of the quantifiers is important. The whole meaning of the statement would change if the order changes. To understand it better, let us see an example again. Considering the predicate q of x, y, which represents the statement x is a man capable of doing a job y. Let us now look at the quantified expression for the same. For all y, there exists x such that q of x, y. This statement is read as for any job y, there exists a man who is capable of doing the job y. On the other hand, if we reverse the quantifiers, the representation becomes there exists x for all y, q of x, y. This statement is read as there exists a man x that is capable of doing any job y. We can now spot the slight difference between both these statements. The same quantifiers are used for both the variables in both the statements, but the change in order changes the structure and indirectly the meaning of the statement. In general, given a predicate p of x, we can restrict the range of variation of the free variable to the domain of discourse D. Mathematically, this is stated by the expression for all x belongs to D, p of x. This is again an example of a universally quantified statement, although restricted to the domain D. This statement would be true if p of x is true for all values of x belonging to the domain D. Also, that this statement would be false if p of x holds false for at least one value of x belonging to this domain. We can similarly define the expression there exists x belongs to D, p of x. This is an example of an existentially quantified statement, restricted to domain D. The statement is true if p of x is true for at least one value of x belonging to domain D. It will be false only if p of x is false for all values of x in domain D. In the next lecture, we will see the impact of negation on quantifiers and De Morgan's law in predicate logic. Thanks for watching this lecture.